Maggie's engine's been rebuilt and it's got 30% more horsepower. Stick around and find out how that happened.
Welcome to another episode of Maggie's Makeover, where we seek to understand if a 65-year-old of modest mechanic abilities can actually restore his 1972 MGB that hasn't run in over 40 years. If you enjoy this content, please like, share, and subscribe to the channel, but more importantly, keep those comments coming because Maggie and I and the rest of the subscribers love to hear from you. As you remember in our last episode, mechanic Steve and race car buddy Kevin Boland successfully removed Maggie's engine, transmission, and overdrive unit. In this episode, we're going to look at what did we have to do to actually rebuild those components. You know, over 50 years ago, when I built this visible V8 engine, I gained a firm understanding of how the internal combustion engine worked. But I got to tell you, I was overwhelmed at the number of decisions that I had to make in this project. Those decisions involved not only the design of the engine, the replacement of the internal components, what machining steps needed to be done, how was the engine going to go and be assembled back together, and more importantly, how do you pick an engine rebuilder and have faith that he's going to accomplish the goals that you set out for and do it at a price point that won't break the bank. You're going to learn all about that in this episode of Maggie's Makeover, so when you go to build your MGB engine, you'll be that much further ahead. To begin with, it probably makes sense to get a basic foundation of how the internal combustion engine works. I got just the guy that I know will do a great job on that. Let's head down to the garage and have a conversation with mechanic Steve. Hey, thanks Studio Steve, and welcome back to the garage, everybody. You know, in 1972, the MG put out just shy of 100 horsepower. Given that the other car that Studio Steve drives is 496 horsepower, I think it's safe to say that we're going to have to tweak some of the internals of Maggie's engine to get just a bit more performance out of it. And in order to figure out what to tweak, we really have to understand the operational cycle of the internal combustion engine. And as you can see here, there are 4 strokes: intake, compression, power, exhaust, or as I like to say, suck, squeeze, bang, blow. The intake stroke begins as the piston begins to travel down vertically, rotating the crankshaft. The crankshaft, which is connected to the camshaft via the timing chain, opens the inlet valve, allowing in a rich mixture of fuel and air. The intake stroke is completed when the piston travels the full length to bottom dead center and the intake valve is closed. The compression stroke occurs when the piston travels from bottom dead center to top dead center, reducing the combustion volume, compressing the air-fuel mixture, and increasing the temperature and the pressure in the cylinder. As it reaches the top, the spark plug is fired, igniting the air-fuel mixture. The power stroke occurs when the camshaft closes both the inlet and the exhaust valve. The combustion of the air-fuel mixture increases the temperatures and pressures in the cylinder dramatically. The expanding gases drive the piston downward. Through the connecting rod, the motion of the piston rotates the crankshaft, thereby turning thermal energy into mechanical energy. The power stroke is completed when the piston reaches bottom dead center. The final exhaust stroke occurs when the camshaft opens the exhaust valve. As the piston travels upwards to top dead center, the exhaust gas is evacuated from the cylinder. The exhaust stroke is completed when the exhaust valve is closed. This complete operational cycle occurs over and over again at thousands of revolutions per minute as the engine runs. So now that we know how the 4-stroke engine works, it's pretty simple to understand how to increase its horsepower, Studio Steve. You've got to get more air and fuel into that cylinder. You've got to compress it to a greater degree, and then you've got to get those exhaust gases out of there. So my suggestion to you is to find an engine rebuilder that knows how to tweak the internals of that 1800cc MGB engine. And no, it can't be the first engine that he's done this on. He's going to have done this over and over and over again, so you know that that job is going to turn out right. And oh, by the way, your distributor, your carburetors, those things are old and tired. They've seen better days. You've got to find some people to rebuild those as well. Hey, thanks Mechanic Steve for those great suggestions. And I got to tell you, I love that guy's enthusiasm, and I'm glad he's working with me on this project. So there's probably a number of you out there right now that are saying, Steve, I know the car was stored for 40 years, but after all, it was in a heated garage. What are you doing rebuilding the engine? Well, I actually posed that question to a number of MG forums on Facebook globally, and more times than not, they came back with the same answer. Don't start that engine. Go take it to an engine rebuilder right away. They had concern that there could be rust on the internals of the engine, specifically between the cylinder and the rings and between the connecting rod and main bearing journals. So when I thought about that, it reminded me of a very famous commercial.
Fran, you could pay a little now or a lot later.
As a case in point, one gentleman I talked to in Florida who did not rebuild his engine as part of the restoration process got pulled over by the state troopers only a month later because his internals in the engine just started to rip itself apart and he was blowing so much smoke out the back end. That's why we've decided to rebuild Maggie's engine during the restoration process and avoid any of that costly damage that could occur to the engine. Now, I spent the last month looking for engine rebuilders in the New England area and online, and I came across a pretty interesting project on a website called MG Experience. On that website are the details behind the rebuild of an 1800cc MGB engine. An engine rebuilder by the name of Dick Moritz and a machinist by the name of Dale Spooner rebuilt that engine and auctioned it for the Make-A-Wish Foundation. And based on that, I decided to give Dick a call and see if he might be the person to rebuild Maggie's engine. Within 5 minutes of being on the phone with Dick, I knew he was the right person for the job. Dick's a pretty interesting guy. He's been in and around English sports cars for the last 30 to 40 years, and he's a certified MG mechanic. Not only has he rebuilt a Jaguar XKE from the ground up, he's also built an MGB race car, which he's pretty proud of. Even in his 70s, he's known to take that car out on the track and put it through its paces. So he spent a couple of hours on the phone with Dick talking about both the stock and the street performance engine rebuild options that he offers. You know, Dick's used the same machinist for over 40 years, and he's done literally hundreds of these engines. More importantly, I learned about Dick's philosophy when it comes to engine rebuilding. He believes that every engine has a story to tell when you disassemble it. What are the shape of those internal components? What are the tolerances between those components that mate together? Dick takes the time to understand that as he disassembles the engine, so he understands what pieces need to be replaced and what machining processes need to occur. He tries to retain as much of the original engine as he can. And best of all, the street performance rebuild option that Dick offers was only $1,000 over the least expensive stock rebuild that I found when I went out and surveyed all of the engine rebuilders. So I separated the engine and the transmission. I cleaned out all that gunk that was in the bell housing, put both of those components on the truck, drove them down to Dick's shop in Philadelphia. It's 4 months later, mechanic Steve is coming back with the rebuilt engine, let's stop down to the garage and have him take us through not only the design of the engine, but how it was machined, how it was reassembled, and what new components are actually in it. You know, great actors always hit their marks, but how many actors can hit their marks with a truck? So after 4 months, I've just come back from a day trip to Philadelphia down to the engine rebuilder, and I'm proud to say Maggies Engine has totally been rebuilt, the transmission's totally been rebuilt, the Overdrive unit has totally been rebuilt, and it's not just a standard stock rebuild. This is a street performance rebuild, 30% more horsepower. So how did we get 30% more horsepower? Let's get this thing out of the truck and go to the drawing board, and I'll tell you how we did that. God, I haven't been in a room like this since my first engineering job over 40 years ago, where we represented our engineering designs in 2 dimensions using paper, pencil, and a drafting board, much like what these guys are doing, in comparison to creating a 3D solid model in the computer that I can just rotate and do machining off of. But in any event, if we want to understand why Maggies Engine now has 30% more horsepower, we're going to have to take a journey into the engine characteristics that actually calculate compression. We're going to look at what did we have to do to that engine to enhance the flow of air and fuel into that cylinder head and the exhaust gases out. We're going to look at a pretty creative trick to use model year piston swapping and a different grind on the camshaft. We're also going to look at what are the machining steps that we had to do to make all of that possible. So there's a lot to discuss. Let's roll up our sleeves and dig in. In this picture, we see the depiction of the cylinder and cylinder head assembly in 2 states. On the left, it's when the piston is at top dead center, and on the right, it's when the piston is at bottom dead center. Now, the compression ratio, CR, is nothing more than the summation of the volume generated as that piston moves from bottom dead center to top dead center, or V2, plus the volume stack up above the piston when it's at top dead center, or V1, divided by that same value, V1. Now, the volume generated from the stroke of the piston, or V2, is nothing more than pi times the bore squared times the stroke of the piston divided by 4. The volume stack up, or V1, above the piston is equal to the volume of the head plus the volume generated from the thickness of the gasket plus the volume generated because the piston actually sits below the deck of the block minus the volume of the piston head. In this case, we see a convex piston head, whereas the MG has concave piston heads. When we think about the output of an engine, we can generate more horsepower by igniting that air-fuel mixture at a higher pressure. Higher compression ratio engines actually do that. Now, when we look at the compression ratio formula, we can increase the compression by increasing V2, or the volume generated from the stroke of the piston, while also decreasing the volume stack up above the piston at top dead center, or V1. Let's next take a look at a couple of engine parameters that directly impact the horsepower of the MGB engine in the model years prior to Maggie. From 1963 to 1971, a 1.5625-inch intake valve was used. When we think about that V1 volume, or the volume stack up above the piston at top dead center, they used a 3/16-inch dish concave piston that measured 6 cc's in volume. They also used a cylinder head that had a 43 cc combustion chamber for a total combustion volume of 49 cc's. This generated an 8.8 to 1 compression ratio in the stock engines from 1963 to 1971. In Maggie's model year 1972 and through 1974, they moved to a larger intake valve measuring 1.625 inches in diameter, thereby allowing more air and fuel into the combustion chamber. They actually reduced the head combustion chamber to 38 cc's. However, they went to a larger dish piston measuring 3/8 of an inch and 16 cc's, thereby increasing the total combustion volume. This had a negative effect on the stock compression ratio, lowering it to 8:1. So when we think about the design of Maggie's new street performance engine, it doesn't take a rocket scientist to figure out that if we could combine the best design aspects of those two previous engines into this engine, we'd have a higher compression ratio engine. And all it takes for us to do is to swap in the shallower dish pistons from the 1963 to 1971 engine into the 1972 engine. This reduces the total combustion head volume to 44 cc's and yields a 9.6:1 compression ratio engine for a higher horsepower output. So what does that physically mean when we rebuild Maggie's engine? Well, we're going to increase V2 by boring out her cylinders 20 thousandths of an inch. And we're going to decrease V1 by skimming her block 3 thousandths of an inch to get to a deck height of 25 thousandths. We're going to skim Maggie's cylinder head 6 thousandths of an inch to true up the combustion chamber to 38 cc's. And as I said before, we're going to install those shallower dish pistons that have a 6 cc volume. To validate Maggie's new compression ratio, I turned to an online compression calculator. You can see here I input all of Maggie's new engine design parameters, and we came up with a compression ratio of 9.65:1. We actually increased the total displacement of Maggie's engine from 1800 cc's to 1822 cc's. In addition to generating more horsepower by moving to a higher compression engine, we can also increase horsepower by increasing the amount of air fuel in and exhaust out of Maggie's cylinders. We're going to accomplish this by opening Maggie's valves more and holding them open for a longer duration. Now, it's actually the profile on the lobes of the camshaft that dictate this. If you look at the graph on the left, you're going to see that it depicts how much those valves are open, or valve lift, as a function of the duration of how long they're open on the x-axis as a function of the 4 strokes of the internal combustion engine. Perhaps a different way of looking at that is the graph on the right, which shows both the opening and closing of the intake and exhaust valves as a function of the angular orientation of the crankshaft. On a stock MGB camshaft in 1972, the lift of that valve, or the opening of it, was 0.265 inches across a duration of 217 degrees. We're going to put a D9 Street Performance camshaft in Maggie that's going to increase that opening from 2.65 to 2.95 inches, and it's going to increase the duration from 217 degrees to 229 degrees. This is going to generate more horsepower in Maggie's engine. We can also increase the airflow in and out of Maggie's cylinders by increasing the size of both the intake and the exhaust manifold ports. Here's a picture of Maggie's stock cylinder head fitted with the larger ported manifold gasket. This gives you an idea of just how much material we're going to remove when we increase the size of those ports. Now, we're also going to go inside each of those ports and polish them to reduce the turbulence of the airflow, therefore allowing more air and fuel into the cylinder and more exhaust gases out, increasing Maggie's overall horsepower. So now that we've discussed the design considerations of the engine rebuild, we need to review the machining processes, the assembly steps, and all the new parts that are going to go in Maggie's engine to complete the engine rebuild. You know, Studio Steve wanted to drag his camera crew through all of that. And if you know him, you know he likes to ask a gazillion questions. And that was going to slow down people like this who are actually doing the work. In fact, when he asked, they simply pointed to this sign on the shop wall that basically told him that it would be cost prohibitive to do so. Now, Studio Steve did obtain some actual pictures of Maggies Engine being assembled, and we're going to use those as well as some of the footage of the machining processes on the Make-A-Wish engine rebuild found on the MG Experience website. So the process began by actually tearing down the engine, and we got some good news in that regard. The block wasn't cracked, the head wasn't cracked, the main bearings were worn but not torn through, and there was no rust on the internals of the engine, although Maggie did need a new valve job. Once the engine was torn down, it was put in a hot tank. Similar to this, Maggie's engine block was dipped in a high-temperature liquid alkaline detergent solution to remove any rust and degrease it. Its internal cooling and oil passageways were power washed to remove any of the sludge that was within them. Both the block and the cylinder head were pressure tested and magnafluxed. Luckily, there were no leaks or cracks in either of them. Next, Maggie's main bearing caps were reinstalled and torqued to spec. The machinist then measured the line bore of the main bearing saddles to ensure concentricity and roundness. Luckily, they were all within spec, and the costly line boring machine process did not have to be done. Maggie's block was then loaded into a CNC machine, and the top of the block was then checked for flatness. It turned out that 0.003 of an inch needed to be removed from the top of Maggie's block to ensure that it was both flat and that it would generate the 25 thousandths deck height from the piston to the top of the block. Although Maggie's piston rings were worn, the cylinder bores were found to be straight and true within specification. Although there was some wear in the cylinders, they only needed to be bored out 20 thousandths over, which is well below the maximum 40 thousandths over. The honing process for each cylinder was done iteratively, 3 times per cylinder with overnight cooling in between, and a measurement done to determine the accuracy of the piston to cylinder bore clearance. This was done measuring the end gap of the piston ring. Given that I religiously changed Maggie's engine oil every 3,000 miles, her bottom end bearings were worn, but only down to the copper, much like these shown from another car. Luckily, Maggie's crankshaft journals all measured within spec. Given that there was no rust or damage, they only needed to be polished, thereby avoiding any costly crankshaft machining and rebalancing. New full-round Durabond cam bearings were installed in the block, making sure that the oil holes in the cam bearings aligned with the oil holes in the block. With that completed, the new Delta 9 cam was trial fit into the cam bearings to ensure that it fit and rotated freely. The original hammered-in type oil galley plugs were removed, the holes were threaded, and the new screw-in type plugs were installed. Finally, the surface of Maggie's engine block was prepared and a coat of primer was applied, thereby completing the rebuild of the block. Given that the original scrape-cut 18V connecting rods are strong yet light, they will be reused. The bearing side of the connecting rods were measured and machined to within tolerance. The new wrist pins were partially pressed into Maggie's new pistons. After heating the piston end of the connecting rods, their final assembly with the piston was done in a vise that ensured proper placement of the wrist pins in the piston. After the head was degreased in a pressure washer and the remaining carbon deposits brushed away, the valves were loaded into a valve grinder and were able to be ground to the proper dimensional specifications. Next, the valve guide and valve stem to valve guide wear was checked and found to be within dimensional tolerances. Pockets for the hardened exhaust valve seats were then bored. The hardened exhaust valve seats were soaked in liquid nitrogen for about 30 seconds. This reduced the press fit from 5/1000ths of an inch down to 2/1000ths of an inch. They were then pressed into the exhaust valve pockets that were previously bored. A 30, 45, and 60-degree angle grind were done on the valve seats to create a tapered bevel fit between the valve and the seats. The head was leveled to 0.5 corner to corner, and a cubic boron nitride cutter was used to take successive passes on the head until 0.006 of the material was removed. This trued up the cylinder head combustion volume to 38 cc's. New valve springs were used in the assembly of the head, and if need be, shims were used to ensure a 90 psi valve spring pressure. Next, the combustion chamber volume of the head was measured and found to be trued to 38 cc's. The work on the cylinder head was completed when both the intake and the exhaust ports were enlarged and polished. The block was prepped before assembly. All of the oil galley plugs were removed and a chasing tap was used to clean them out along with any other threaded hole. The block was then cleaned and painted a final coat of black. The piston rings were then installed on the pistons. The oil scraper ring was done by hand first, followed by the compression rings, which were put on using a ring expander. Finally, piston ring side clearance was checked and found to be within specification. With the assembly of the pistons now complete, it was time to move on to the trial assembly of the engine to validate the tolerances between some of the main components, starting with the crankshaft. The oil passageways of the crankshaft were cleaned out with carburetor fluid and pipe cleaner. End play of the crankshaft was validated by placing the crankshaft in the engine block and tightening the 3 internal main bearing caps after the installation of King tri-metal bearings and the thrush washers around the center main bearing. Using a dial gauge, the crankshaft end play was measured and found to be within tolerance. The tolerance of the 5 main crankshaft bearings were then evaluated by first removing the end caps of the 3 central main bearings that were previously assembled. A small extrusion of Plastigauge was placed on each of the crankshaft journals, and then all of the end caps were torqued to spec, including the front and the rear. Upon disassembly, the width of the compressed Plastigauge showed that the tolerance of the 5 main bearings of the crankshaft were within specification. After the cylinder walls were cleaned, the cylinders and piston ring assemblies were lubricated with engine oil. A piston ring compressor was used to seat the pistons in the cylinders. A small hammer was used to tap the pistons down into the cylinders. Connecting rod bolt guards were used to ensure that the crankshaft journals were not damaged. Connecting rod bearing tolerances were checked in a similar fashion to the main bearing tolerances. Plastigauge was placed on the crankshaft journals, while the connecting rod end caps were torqued to spec. Upon disassembly, the Plastigauge showed that each of the connecting rod bearings were within specification. All of the steps for the successful trial assembly were reversed. All of the parts were cleaned and then reassembled. Again, engine oil was used for the cylinder walls and the piston rings, while this time a thick red assembly lube was used both on the connecting rod bearings and the main bearings. The gear on the Delta 9 camshaft was lubricated with white lithium grease. The camshaft was slid into the engine and red assembly lube was used on the camshaft bearings. The original Hober-Eaton oil pump was cleaned and found to be within spec. It was packed with petroleum jelly and its gear drive was lubricated with white lithium grease. The front plate was mounted to the engine block. Next, a double roll timing chain assembly was installed. This included the chains, sprockets, and tensioner. Red assembly lube was squirted down into the camshaft lobes. It was also applied to the new tappets or lifters before they were inserted into the block. After the head studs and gasket were installed, the head was assembled onto the block. The push rods were dropped in and the rocker arm assemblies were installed. Both of those were lubricated with engine oil. After the valve lash was adjusted, the valve cover was put on using a new gasket. The worn surface of the rear crankshaft was covered in a speedy sleeve to reduce oil leaks. A new rear seal was installed in the backplate and the backplate was mounted to the engine. The original flywheel was turned and a new heavy-duty Borg and Beck clutch and throwout bearing assembly was installed. A Moss Motors 16164N replacement starter was purchased along with a classic gold water pump and gasket. Both the intake and the exhaust manifolds were degreased, media blasted, and painted with a high temperature paint. The transmission was disassembled, cleaned, and then reassembled, replacing the following items: the input shaft bearing number 5 in yellow, as well as the first and second gear, third and fourth gear synchros number 35 and 44 in blue were replaced. The lay shaft roller bearing number 16 in orange was also replaced. The front seal number 2 in pink and the rear seal number 58 in pink were also replaced, along with the many gaskets labeled number 3 in green. After the assembly, the transmission was painted silver. The overdrive unit was disassembled, cleaned, and then reassembled, replacing the following items. The cone clutch thrust bearing number 54 in blue was replaced, along with a number of O-rings starting with number 32 through 84 shown in orange. The gaskets number 39, 76, and 87 in green were replaced, along with the two seals number 24 and 31 in pink. The overdrive unit was then attached to the transmission, and that assembly was then mounted onto the engine block. Maggie's carburetors are 51 years old, and they've been sitting for over 40. When they were removed from the car, they were pretty dirty, greasy, and grimy. That's why they need to be rebuilt. God only knows what's in those float bowls. As I was looking for somebody to rebuild Maggie's carburetors, I came across a gentleman by the name of Joe Curto. Joe's been in the business of repairing carburetors for British cars since 1980. He's the world's foremost authority on carburetors for British cars. In fact, in recognition of his work, in 2018, he was inducted into the British Sports Car Hall of Fame. He actually manufactures his own replacement parts, including throttle shafts, jets, seals, and fuel lines. Not wanting to use a set of rebuilt carburetors off the shelf, I opted to wait the 5-month backlog for Joe to personally rebuild Maggie's carburetors and return them. The carburetors were rebuilt from the inside out, including refinishing the external surfaces. It was well worth the wait, and I can't wait to put these on Maggie's engine. Like Maggie's carburetors, her distributor had seen its better days. When we took it off the engine, it was pretty grimy, and it was clear that it needed to be rebuilt. I chose Jeff Schlemmer with Advanced Distributors to do the rebuild. First, it was disassembled, cleaned, and machined to remove any play in the components. Its parts were polished to the desired finish and reassembled. The old points and condenser were replaced with new parts. Next, the distributor's springs were replaced to tailor the mechanical advance along the engine's revised ignition curve, given the new compression ratio and use of a performance cam. More mechanical advance was provided at lower RPMs to maximize Maggie's acceleration. Validation testing of the performance ignition curve was done on a Sun testing machine. And with that, Maggie's engine has totally been rebuilt. For historical purpose, here's a list of all the new parts that went into Maggie. I'm told by the engine rebuilder that Maggie's odometer should be able to go another 75 to 100,000 miles on this rebuilt engine before it needs to be touched again. The final specifications of the engine rebuild are shown here. Given that we're actually beginning to spend money in the restoration process, I thought it would be interesting to track that from episode to episode. Hopefully this helps you when you think about your own restoration process and where and how you want to spend the money. You know, a big fan of Maggie's by the name of Ron came up with a great analogy to present this in, the speedometer. So let's take a look at where the spend has been to date. The total restoration cost for this episode is $7,644. The majority of that was spent on the engine, transmission, overdrive, and carburetor rebuild. The remaining costs were split between other items that were purchased or rebuilt that are shown here. So that's a wrap for this episode of Maggie's Makeover. Hopefully you found this episode both interesting and helpful should you decide to rebuild your MGB engine. As always, Maggie and I and the rest of the subscribers would love to hear from you in the comments section below. Stay tuned for our next episode where mechanic Steve replaces the 50-year-old fuel tank on Maggie. Until then, happy motoring. Hey, Mr. Director, is there any way I can seriously take some of this cash home with me off the set? Okay, this is like take 4. I'm backing the truck up. I mean, you either center this truck and do a good job, get your lines straight, make sure the camera's working, or you go home.